Heyo y'all, this is Chrissy coming at you with our third installment of Not the Ideal Medium for Teaching Physics. We're going to be talking about Chapter 19, Optical Instruments. We've been talking about different models of light. Chapter 17 treated light as a wave, and Chapter 18 treated light as a particle. Now, we're going to more or less abandon the use of both of those models and just talk about light in everyday objects, such as eyeglasses, cameras, and telescopes. My knowledge of biology is primarily trivial, but I would imagine this would be helpful in fields like optometry. I know that it has implications in astronomy, using microscopes, and being a 15th century pirate. We'll start out with cameras. A camera is basically a light collector with a focusing lens. Light comes in through a lens and sort of stains a photographic paper. The more light that hits a spot, the more stained that spot is. That means that it's brighter. The F number of a camera or any optical system is its light gathering ability. This is the ratio of its focal length to the diameter of the lens. Or we say that the F number is equal to F over D, where F is the focal length and D is the lens diameter. A small F number, also called an f-stop, lets more light in. It has a larger diameter. A large f-stop lets less light in. The same principles apply to the human eye. Our eyes are a single lens system that I understand primarily mathematically. Our perfect vision is based on the optimal shape of an eyeball. Normal vision, we say, has a near point of 25 centimeters. At least it's 25 centimeters in adulthood. Our far point is infinity. Your near point is the closest that something can be to your eye that you can still see clearly. Slight tangent. When you're younger, your near point is often closer than 25 centimeters. It's usually actually closer to 10 centimeters. I'm nearsighted. So if you're nearsighted, your near point is actually closer. I measure mine at about 8 centimeters. I know that this is a weird flex, but let me have this. I can't see far. To find your near point, you can hold a ruler right next to your eye. Then bring something as close as you can to it where you still see a clear image. That's where you find your near point. End of tangent. Most people need glasses at some point in their lives. This is usually due to a refraction error in the eye, or presbyopia. I think I'm saying that right. Presbyopia presents in two different ways. The first is hyperopia, or farsightedness. This is someone who needs reading glasses. It means that your eyeball is actually too short. This can be fixed with a converging lens. Myopia, or nearsightedness, means that your eye is too long. This is corrected with a diverging lens. When someone is farsighted, their eye is too short. That means that light rays come in from an object and they actually converge at an area that would be behind your eye. So they actually hit an area that is in front of where they're not converging, which is why you see a blurry image. Eyeglasses give you a virtual image that converges at the right point. So if you look at this first one, you'll see that actually all of them are meeting at a point that's behind your eye. If you are nearsighted, then your eye is too long. The light rays come in and they converge at a point and then they keep going, which is why you see a blurry image. So if you make a lens, you can then make it so that they all converge at the right point. You see correctly when all of the light rays are converging on the back of your eye or your retina. In eyeglasses, the refractive power of a lens is related to its focal point. A lens's refractive power is the power is equal to 1 over f, where f is the focal length. The SI unit for refractive power is the diopter, the diopter. I actually don't know how to say that. The diopter. That is represented by a capital D, and it is equal to 1 over a meter, or an inverse meter. The power and the focal length are inversely proportional. A monkey you found has hyperopia. The near point of his left eye is 150 centimeters. What prescription lens will restore normal vision? For the sake of argument, we're going to assume that monkeys' eyes are like humans. Assume the near focal point for a normal monkey is 25 centimeters. So we would say that S, our object position, should be equal to 25 centimeters. The monkey you found is going to have a near point of minus 150 centimeters. So we say that S prime is equal to minus 150 centimeters. The S prime, or image position, is always going to be negative when doing glasses. This is because the image is going to be on the same side as the object. So make sure that your S prime is negative. We need a lens to refract the light to create a virtual image at 150 centimeters. This sounds more complicated than it is. We're going to use our big equation from the last chapter. 1 over S plus 1 over S prime equals 1 over F. Our S is 0.25 meters. That is our normal vision. Our S prime, where we want our image to be, is minus 1.5 meters. This is our monkey vision. We can plug these in. 1 over 0.25 plus 1 over minus 1.5 is going to equal 1 over F do the math and we get 1 over F is equal to 3.3 inverse meters. Remember that power is equal to 1 over F. So another way of saying this would actually be 1 over S plus 1 over S prime equals the power. Since power equals 1 over focal point, which equals 3.3, we get that our power is 3.3 diopters. We will pick this back up in part 2. See you then.